Welcome to the content material for Class 7 of Engineering Statics. You should be watching this video before your 7th class. In this lesson, we will talk about how to draw free body diagrams of particles that are in equilibrium and how to solve force systems using equations of equilibrium. We have learned how to add forces and determine the angles between forces. Now it is time to put those skills to use. In this course, we are studying cases where an object is in equilibrium. If an object is in equilibrium, it means it is not accelerating. It is either sitting at rest or it is moving at a constant velocity. When an object is not moving, we call that static equilibrium. If an object is not accelerating, it means the sum of all the forces acting on the object is zero. This equation is very useful to us. However, to use it, we have to first identify all the forces acting on an object. We do this using a free body diagram. A free body diagram is a drawing that shows an object and all the forces acting on the object. Here is how we do it. First, select the main object that you are looking at. In this case, we are looking at this 5 kilogram weight. It has two cords holding it. When we draw the free body diagram for this weight, we see that there is its weight from gravity pointing straight down. Then there are two forces, which we will call TA and TB, pulling upward. So here is our free body diagram of this situation. For now, we need to know two things that can attach to our object. The first connection is a cable or cord. We will assume that the cable and the cord has no weight and cannot stretch. These cables can only support tension. In other words, if we push on the cable, it cannot hold any force. If a cable passes through a pulley, the magnitude of the tension force in the cable is the same everywhere in the cable. So in this case, the force T is equal, since this is a single cable passing through the pulley. The second type of connection is a spring. A spring can stretch, and the more the spring stretches, the stronger the tension force in the spring. Have you ever tried stretching a spring? The farther you stretch the spring, the harder it is to pull. Therefore, the force in the spring is proportional to the length of how far it stretches, S. So the force F is equal to a constant K times the length that it stretches, S. Every time you see a spring, you will use this equation. For example, let's say that this spring has a length of 0.8 meters when it is not stretched. Then we stretch it and the length becomes 1 meter. Let's say we also know that the constant for the spring is 500 newtons per meter. So let's find the force, F. First, we have to know how far the spring stretched. We know that it stretched 0.2 meters, from 0.8 to 1. Then we multiply by the constant K, and we find that the magnitude of the force is equal to 100 newtons. Let's look at an example of how to draw a free body diagram. Okay, so in this example, we have a sphere that's hanging from a cord, and that cord has a spring attached to it. So what we're asked to do is draw a free body diagram. And we can actually draw a free body diagram for each of the objects that we see. So first we can draw a free body diagram for the sphere. And when we do that, we see that we start with the sphere, and we know that it has some weight pointing down. We know that weight, we'll call W, is equal to the mass times the gravitational constant. And we know pulling in the opposite direction is the tension in the force along the chord CE, which we'll call TCE. Now if we draw a free body diagram for the chord, that's CE, we see that there's on each end a hook or an attachment. And we know that the tension force TCE is pulling in opposite directions. And finally, if we draw a free body diagram for the attachment at point C, we know that again the force is pulling down that tension from the chord CE. We know that the spring is pulling directly to the right, and I'll call that the force CD, and we know that that's equal to the spring constant times how far the spring stretches. And we also know that there is some force or tension pulling along the line CB. And we're told that that goes at a 60-degree angle. And so we would be able to use this with some information. We'd be able to use this free body diagram to then later solve based on our equations of equilibrium. Now that we know how to draw a free body diagram, how can we use this? Well, if we know that a particle is in equilibrium, we know that the sum of the forces is equal. Specifically, we know that all the forces in the x direction are equal to 0, all the forces in the y direction are equal to 0, and all the forces in the z direction are equal. Then we use our skills at making Cartesian coordinates to break up any forces into the x, y, and z components. Then we solve these equations. It's important to carefully watch your plus and minus signs. You need to define what you call positive. For example, if I draw this free body diagram for this particle, and I draw it like this, it means that I can call this 10 Newton force as positive because it acts in the positive x direction. However, when I draw this force F, I'm also drawing it in the positive direction. So I will make my equation like this. F plus 10 newtons is equal to 0 for this particle to be in equilibrium. Once I solve for F, I find that F is equal to minus 10 newtons. That means that F actually points in the opposite direction of the way that I drew it, like this. Let's look at some examples. Okay, so in this example, we see that there's a weight hanging, and we're told that the weight has a mass of 60 kilograms. And we're given the angles and the direction that the chords AB and BC point. So we see that the chord BC, for example, is at a 45-degree angle. And we're asked to find what is the tension in chord BA and what is the tension in chord BC. So, the first thing we have to recognize is that if we look at the weight, we know that the weight is pulling down and that the only other force acting on that weight that's hanging there on the cylinder is the force BC and from the chord. So we can see very clearly that the tension in the chord BC is going to be equal to the weight. So we can already solve for that. We can plug those numbers in. We know that it's a 60 kilogram mass. We multiply it by times 9.81, the gravitational constant, to find that the tension must be 588.6 newtons. But the real free body diagram that we need to draw is going to occur at the point B. So the connection at point B, we know that there's some force in the chord BC as well as in the chord BA. And we have this tension in the chord BD. We know that this is at a 45-degree angle, and we know that this goes over 4 for every 3 that it goes up. And we'll be able to use that information. So, as we're going to do in most problems, we're going to start by setting the sum of forces equal to 0. So, the sum of the forces in the x direction is equal to 0. I'm showing that positive is defined as going to the right. So if I see that the force points to the right, it'll be positive. If it points to the left, it's negative. So I see that in the x direction, there are two forces. There's TB, TBC, and there's TBA. These each point to in the x direction, whereas TBD does not point in the x direction. It only points in the y direction. So let's put in the positive forces first. So TBC, the x component of it is the cosine of 45 degrees, since we have that triangle. So 45 degrees, this is TBC in the x direction, TBC in the y direction. In the negative direction, or pointing to the left, we have the force TBA, and that's 4 over 5, again based on that triangle, is equal to 0. In this case, we can solve for TBA as equal to 5 over 4 times the force BC times cosine of 45 degrees. Okay, now we still have two unknowns. We don't know how to solve that, but we do have a second equation. We can set the sum of the forces in the y direction equal to 0, and again defining upward as the positive y direction. So look at the y direction, we have three forces. So in the upward or positive direction, we have T, B, C, and we need just the sign of that. We have another positive direction, which is TBA, and that's going to be 3 over 5. And then going down, we have TBD. So be sure that this is negative here. Be sure that this is negative. Okay. So here we can use this equation to insert into this equation. When we do that, we see that TBC sine of 45 Now go ahead and solve for TBC. Because at this point, everything over here is known. So I can solve for TBC. And I plug in what we know. We know that TBD, we solved for that already, is equal to 588.6 newtons. And divide by all of this. When I do that, I find that TBC is equal to 475.7 newtons. And I can go back to this equation where I say TBA and I find that TBA is equal to 420.4 newtons. And that's what we're looking for. In our next example, we're going to include a spring. So we see that there's a spring on the right-hand side, a cord on the left-hand side that's holding up a lamp. And what we're asked to find is what is the length of the cord AC. So the first thing we do, as we always do, is to make a free body diagram. Now choose the point A. And we know that there's the weight of the lamp pulling down. There's the force of the spring pulling to the right. And there's the force of the cord, AC, which is pulling at a 30-degree angle, we're told. And there's a few other things that we can also say. We're told that this length here is 2 meters. So we know that this length here is 2 meters. And we know that there is the length of the cord, the x component of the length of the cord AC, which is equal to the cosine of that angle, 30 degrees. And over here is the length of the spring as it's been stretched out. And the length of that spring is its initial length unstretched, which we'll write like this, plus how far it stretches. In other words, the length of the spring is equal to its initial unstretched length plus how far it stretches. And we know that all of this is equal to 2 meters. Okay, so we're going to need that equation later on to be able to solve for what we're looking for. We also know that the spring constant K is equal to 300 newtons per meter, and we're told that the unstretched length of the spring is 0.4 meters. Okay, so now that we've made our free body diagram, we've written down our known constants, and we've put together our equations. The next thing we need to do is our equations of equilibrium. So we start with the x. Again, to the right is positive, and we know that in equilibrium it's equal to 0. So the force of the spring is to the right, so it's positive, and in the left hand direction we have the force, the x component of the force along the cord AC. If I solve for the force of the spring, I see that these two are equal. The next thing I'll do is solve for the y direction. So pointing up, positive, we have the tension in the cord AC and sine of the angle. And downward we have the weight of the lamp. So again, we see that the weight of the lamp is equal to the tension in the cord, the y component of it. Well, we do know what the weight of the lamp is. We're told, so we can solve for the tension AC. It's equal to W over sine, which is equal to 8 kilograms. We're told the mass is 8 kilograms times 9.81, the gravitational constant, divided by sine of 30. When we solve that, we see that this is 156, about 157 newtons. Now, we know that we can go up to this equation up here and put that information in and find the force of the spring. 156.96 newtons times cosine of 30. So we see that the force of the spring is 135.93 newtons. Well, we know that in a spring, the force of the spring is proportional to how far it's stretched. So now we know how far S is. S is equal to the force of the spring divided by that constant, which we know. So 135.93 newtons divided by that constant, which we're told is 300. So 300 newtons per meter. When we solve that, we find that it's 0.453 meters. We're almost there, so we go back up to our equation here. So we find that the length AC, solve for LAC, when we solve, we find that the answer is 1.32 meters. And that's what we're looking for. So in the last example that we're going to look at in this video, we're going to do this in 3 dimensions. So now we have the x, y, and z directions. So the first thing I'll do is my free body diagram at the point A. I know that there's the weight of the crate or the box, which is equal to the mass times the gravitational constant. And that's going downward in the y direction. We know that there's a force of the spring pointing in the positive x direction, and there are 2 chords. So I'm going to call them tension in the chord AD and tension in the chord AC. And what we're asked to find is what is the force in each of these chords. So we need to find what Fs is, what TAC is, and what TAD is. Well, as usual, the first thing we want to do is write down what we know. Well, we know that the mass of the crate is 100 kilograms. We know the spring constant is equal to 1.5 kilonewtons per meter. And we know some angles of the chord AC. So I'm going to call that alpha AC from the x direction, from the x-axis, we're told is equal to 120. Beta from the y-axis is 135 degrees. And gamma from the z-axis, we're told is 60 degrees. And we also know the direction of the chord AD. So I know the magnitude of that directional vector is equal to the square root of each component squared. And we see that that is equal to 3 meters. And so the directional vector in the chord AD is equal to negative 1 over 3 in the I or x direction, 2 over 3 in the positive y direction, and 2 over 3 in the positive z direction. So we're going to establish each of our vectors now. So the vector of the force along AB, we know is just the force of the spring, and that acts only in the x direction. So that's this force right here. The force along the chord AC has multiple components, so it's going to act in the x, y, and z direction. So we need to break that up. Well, we're told the angles, so we're going to go back and use the cosine of alpha for the x direction, cosine of beta in the y direction, and cosine of gamma in the z direction. Now I want to find the force along AD, and that's why I found this directional. So it's the magnitude of the force times its direction. And so when I plug that in, I can see that that's 1 over 3 in the x direction, 2/3 of the whole. And lastly, we have the weight vector, which we know points downward in the z direction. Now what I want to do is I want to do the x, the y, and the z. So I'll start with x. So I'm looking for only the x components right now. So I see x here, here, in here. So we have the positive Fs plus TAC cosine minus is equal to 0. Now the sum of the forces in the y direction are equal to 0. So now I'm looking for j components. So no j components here, j and j. So here we have TAC and now we wanted to do in the z direction. So here, so at this point I have equation 1, equation 2, and equation 3. And the first thing that I can do is I can look for the easiest one to solve. So I can see that this one only has 2 components. So I'm going to solve equation 2. I'm going to solve for TAC. So with equation 2, I see that TAC next I can put that information into equation 3. And now I want to solve for all of these values. I'm going to compute these values. So when I do that, I see that's 0.4714 plus 0.667 equal to 100 times our gravitational constant. So I can now see that TAD, when I solve for it, is equal to 862 newtons. So after I solve for TAD here. Now I'm going to bring that information back to equation 2. And I can solve for that. I see that now I have one of the values, two of the values. I'm only looking for one more. So I can finally go back to equation 1. Equation 1 tells us the force in the spring is equal to 1 over 3 TAD. Plug the values in. Now interestingly, cosine of 120 degrees is negative. So this will actually become positive. So we'll see that the final value is that the force of the spring is equal to 693.7. So I'll go ahead and write all the answers here together. And there we go. So that's it for today. Be sure to look through these examples and be ready for a quiz on this material in Class 7. See you then.